Hi, everyone. Welcome to today's masterclass on object-oriented programming. Thanks for joining me. I'm hoping today that you're either in one of two categories. Either you're using MATLAB, but you think you need to start learning about object-oriented programming, or perhaps you come from another language that is object-oriented and you want to see how to do it in MATLAB. For both of those sets of people, I'll be trying to show you what's going on today. So thanks for joining me. My name is Loren Shure, and I've worked at MathWorks for over 30 years, and I try to share my knowledge in classes like today's. You might also find some interesting MATLAB tips on the blog that I maintain on the MathWorks website, The Art of MATLAB. So let's get started. Okay, so as I said, the topic is object-oriented programming with MATLAB. And my agenda is basically why bother with object-oriented programming? We can get everything done or most everything done without it. I'm going to make sure that for those who are new to this area, that I talk about the basic concepts and terminology. And I'll show you how to make a class. It's pretty easy. And then how to make classes more robust. And I'll show you what I mean when I get to that. And I'll just talk in general about more advanced features that are available that we won't have time to go through today, really. So the problem I want to talk about is finding and locating balloons or blips from radar that's been deployed up in some balloons, basically. And I have a sensor array that's going to do this. And you can see what I have here is that I have two that are staying at about minus, I don't know, whatever, minus 30 degrees and minus 45 degrees and maybe minus 50 degrees. And then I have this other one that's moving. And as we go over time, you can see that it's being detected and identified, different number of targets at different times. And so I would like to show you as an example how I use that and a bunch of different programming techniques for working on it. So the first thing I want to do is talk about the progression of different techniques. So whenever we're talking about an algorithm and something like this, we have data as well, and we need to combine the two. The algorithm has to actually work on the data to make this make sense. And so we might have values, like I might have $10 in my checking account. And at the command line, I might say, tell me the interest on my $10, and I multiply by 0.00000001 and find out, of course, that I get nothing. But I don't need a fancy program for that. And that's not something I do every day. I don't need to automate it. There's not a big deal with that. But as things get more, as I'm trying to solve a deeper problem, I might want to take advantage of increasing sophistication. And so it's not that hard, but I might put some data into a variable, and I might use that variable in a script. And I, might have a whole bunch of lines of code in order to analyze those data. And I might want to say, well, I don't have just one variable. I actually have a bunch of variables that are related. So I might put them together in a table or a structure or something like that. And I might operate them on them with functions, knowing that I might have another set of data coming along later, and I want to reuse this algorithm that I'm creating on new data over time. And then finally, we get to classes. And classes are an interesting construct because, well, you'll notice up here in the beginning, when I was talking about the programming techniques, the data kind of sat on their own, and the programming, if you will, the algorithm sat on its own. But in a class, we actually join them together. And classes have basically the algorithm piece, which are called methods in object-oriented programming. And the class also has data associated with it, and those are called properties. And so the scenario that I'm looking at is a sensor array, and you can see the array of sensors here that are going to try to locate a weather balloon that's transmitting a signal. And the sensor array receives these different blips over time, but of course they don't all arrive at the same time because they're spread apart. So this one might, if this was the nearest one, it'll come to there first and maybe there next and so on. And our goal is to process the blip in such a way so that we can compute the angle of arrival. How far is away and what angle, is the blip here or is it somewhere over here, for example, in which case the arrivals would come in a different order, maybe in different sequence. And so that's the problem that I want to try to solve here. So how can we implement this scenario and how can we make it robust? So I'm going to come over to MATLAB now, and I'm going to show you what I would do with a regular procedural program. Only I have enough code here that I am not going to type a whole lot here. I have stuff already written. And what you'll see here is I have my script here. It's a live script. So I've got, or it's a regular script rather, and I've got my comments here, and I can just run a section. If I come to the editor, I can run a section. I use run a section in advance so often that I have a copy of it on my quick access tool strip here, toolbar. And so I'm going to run a section. I'm just going to make sure I have nothing in my workspace. And now I'm going to define the signal that it's sending. So if I come back to this picture, this is sending a signal. Well, what's inside that signal? What's inside that signal is, well, in order to do what we need to do, we need to know what the speed of light is, because I'm going to take that with the frequency of the signal that we're using and compute the wavelength. It has a certain wavelength, and I'm going to give it an amplitude. So that's what our signal consists of. I mean, those are the specs for the signal. That's not the signal itself. And then I need to define, right now, we want to eventually find out what is the angle of attack or the angle of arrival. But right now, I want to assume I know it and do the problem in the forward direction. Eventually, we want to go backwards and solve what's called the inverse problem. So I'm going to have a balloon at an angle of arrival of -10. I'm going to say its range, its distance from here is really, really big. It's basically infinitely far, kind of. Not really, but pretty big. And then I'm going to embed in the balloon the signal. And so now I have something that's called a structure. So if we look in my workspace, I've got two different structures, and I can click on one of them. And you can see that this is a structure, the balloon, and it has 3 fields. Now, in this case, it has a single value, the angle of arrival. We happen to see it here. The range, 1 times 10 to the 10 to the 8th, and then embedded in there another structure. So basically, a structure allows me to combine data that belong together, but don't necessarily fit together like in a vector or in a matrix. Or even if I could, it might be inconvenient because they're different units or something like that. Okay, and how do I index in? Well, if I go like this, let's just go like that, you'll see that I index in here by saying balloon dot AOA. So dot is the way I index into a structure and find the value of a field in the structure. Okay, so that's what a structure is, and many of you probably know what that is. I'm not going to add any extra balloons right now. I'm going to skip that, and I'm going to define my sensor array. And you can see it has a whole bunch of parameters that I need in order to try to figure out how to make it work right. It's got number of detectors and number of samples and 0 padding, because it's actually going to use an FFT algorithm underneath. And from all these specs, from the balloon and the sensor, I'm going to actually make what the signal would be coming from that balloon based on that sensor, what would arrive at that sensor. And I'm going to get the array data from that. And from the array data and the sensor information we have, and I can show you, I've got this here. It's a whole bunch of FFTs and things like that. But you can come here, and now I can say, calculate the angle of arrival based on this. We knew what it was to begin with. It comes back and tells us it's at an angle of -9.5. Well, if you recall, I made it an angle of -10. So I might want to figure out whether, even before I do something in the field, if I want to have, maybe instead of having my number of detectors be 16, maybe I'm willing to spend money and make, 3,000 of them. But before I do that, I might want to do an experiment numerically to figure out if that's going to help me. So let's just work with the FFT, the sensor 0 pad first. And let me come in here and make that 256. And I'm going to recreate the data because I changed the sensor. And here's the angle of arrival. And it did get better. And you can see I have a 2048 there. I'm an impatient person. So I'm going to go right to the value that we found was really good for the 0 padding. And now I come here, update my data, and I get a much closer value, closer to -10 than I had before. And you can see it over here in this plot, which is showing where our peaks are the angles at which there are potentially different arrivals. And we can see one here at around -10. Well, maybe that's not quite close enough for me. And I go, well, what else can I throw at it? I don't really want to do a longer FFT because maybe that will introduce too much latency into the calculation. And I want to be able to keep track of these things very fast. And so maybe I can change the number of detectors. So I can say sensor.num detectors equals, I had 16, I'm going to make it 32. Since I changed the sensor, I need to recompute the signal, and I need to recompute the angle of arrival, and it didn't change. The number of detectors, the more information I have from more different bases on the ground, it's not helping me in a finer way find that, well, let's just try this again. Maybe 32 wasn't enough. Maybe I should do 1024. I mean, this is just a simulation, right? So why not? It didn't change it at all. Well, let me come back up here and remind us we also had our signal speed of light. One of the dangerous things about using structures and procedural programming is I could say signal dot. And by the way, if I just do dot, I can hit the tab key and find out what's in there. So I can change the speed of light equal to 33. That's not really good. I'm going to come up here and actually reset it because I don't want to mess that up. But you can see that I'm not safe that way. So why didn't this work? Well, I'm going to show you why it didn't work because I cheated, and I'm going to open up a sensor. And now you're going to see that my original field was called num detector, and I wrote num detectors, and it just added another field. It didn't warn me, it didn't tell me, it didn't give me an error message, anything. And so I'm a little bit unprotected. I can do everything I want. It's sort of the Wild West, but there's nothing to put checks and balances on me at that time. So it's a little bit scary. It's very flexible, but things can go wrong. So let me come back to the slides for a moment. So as I said, it's pretty easy to learn. We kind of didn't have to plan. We could think about, oh, well, what if we added this new parameter? Maybe that would help. And you get to try things really quickly. And there's no formal relationship between the data and the functions, though. I'm not making sure that I'm not doing any sanity checking. And you see every single thing in that sensor. And maybe some of those things aren't available. Maybe I'm going to switch a sensor someday, and not all of those things are going to be available. So I could have a problem if that were true. I'm going to come here while I'm at it and change this to 96. And then I'm going to rerun this sensor. And I don't get much closer. But now what happens is let me actually change that back for a moment. Let's leave that at 16 for the moment. Whoops, 16. And now what I want to do is I'm going to add 2 more targets. So our signal is going to be a combination of balloon number 1, balloon number 2, and balloon number 3. And you can see instead of at -10, I have one at 20 and one at 25 that I'm adding. And now I'm going to just set up my sensor array, compute the data, compute the angles of arrival, and display the, and now you see it doesn't find 3, it finds 2. And oh no, it only finds 1 here. That was left over from before. It finds this biggest one here, but this peak even is enough lower that it decides it's not important enough. And that's again because at this point I don't have the right number of detectors. So let's see if we can do better with the more detectors that we have. Let me run that, create the new sensor data and the field data. And now you can see I get 3 balloons minus not quite 10, not quite 20 and 25. And here you see on my plot, I get the 3 different targets that we were looking for pretty closely now. Again, but this was without doing anything formal to make this all work. Well, that may be uncomfortable to a lot of us. You know, then you could start putting all kinds of error checking in the program, do that. But if you miss anything, maybe it's so obvious to you that the speed of light is what it is that you don't even think to make sure that someone can't change it by accident for the purposes of your experiment. So what I said before was that there was this progression of programming techniques, and now I'm ready to think about using a class to help me out here, to help me not make the kind of mistake, if you will, when I put num detectors instead of num detector in there. And let me give you some background on object-oriented terminology, and this is general object-oriented technology, not MathWorks specific. A class. You might also hear it about class programming. Classes are a blueprint for creating an object. It's an idea. Classes also contain properties that are data and state related, and behaviors, which are algorithms or behaviors or actions. An object is a specific instance of a class. So if I have a class called dog, the properties for that class might include breed, age, color, and the things that can happen with a dog are eat, sit, and bark. Now, here's 2 instances of dogs, my pal Sean's dogs, Lexi and Luna, and you can see they have data behind them. They have Alaska Husky, she's 8 years old, she's black and white. And well, this isn't Sean's. I don't know whose Luna is, but Luna's a Chihuahua. She's age 4, and she's brown, and they can both do the same things. They can eat, sit, and bark. But the way they do that, of course, is different. Lexi may bark in a much less high frequency bark most of the time than a smaller dog, a Chihuahua. So they don't do it exactly the same way. They don't get the same value, the same outcome. But once you put their properties in, you can do modeling and predictions. So what I want to do now is I want to define a class that's a blip. And from that class, I want to create a balloon object, and I want to use that object in place of the structure that we have. So let me just come back here. And what I'm going to do is I'm going to come to the Home tab, and I'm going to say I want a new class. And MATLAB opens up this file for me. It's basically a template. I'm going to double click here and show you the whole thing right now. And I'm going to make it of a class blip. And I'm going to put some help in here. Blip. Simple blip class. This is why you don't want me typing, because even on something as simple as that, I make a mistake. Yada, yada. You hopefully will use something more meaningful. And now what properties do I have? Well, what did I have before in my balloon? If we look in my balloon here, my balloon had AOA, the angle of arrival, the range, and the signal. So I'm going to come over here and I'm going to put AOA, range, and signal. And at the moment, I'm going to delete everything else, because that's all I got. And I'm going to put an end at the end because the code analyzer was telling me to, and because it's the right thing to do. Let me just, okay. And I'm going to save this. Whoops. And I'm going to save it to Blip. Now, what can a Blip do? Well, I can say whoa. My keyboard got enthusiastic there. My keyboard is being sneaky at the moment. It's not letting me do anything. One second, sorry about that. We'll be back in a moment. Oh, it will let me do this. I can cut that out. And now, come on, keyboard. You can do it. I don't know. All my equipment has a mind of its own today. Come on. So sorry about that, folks. For a moment, my keyboard quit working and now it's working. So B equals Blip. And you'll notice that Blip doesn't have any values, but I can then say B dot AOA, and I could say equals -10, and B dot range equals whatever range I had before, I think. Nope. Oh, yeah. It's wherever it is. Let me come back here. Range. Let me go like that. Copy. That was because it called the range function in MATLAB instead of what I wanted. B dot range and B dot signal equals the signal we have. So now if I look at B, it's got all this stuff in it. And if I say, well, let me start with something easier. Let me make an A. A equals 17, str equals string. I can say, is it a string? Whoops. And it's not. You already know about classes, even if you didn't think you knew about them. Is it a double? Yeah. Is it a float? Yeah, it's floating point because floating point is double or single. Is it numeric? Numeric, yes, but it's not a string. And I can do the same thing with string, and I can say, is it a string? Yes. Is it a character array? Nope. Is it a cell array? Because we used to put strings into cells and cell arrays. Nope. So now I can say, is a B, my blip, is it a struct? No. But you saw I'm addressing it like it is B dot AOA and so on. But if I print out B, you'll see that it's a blip that has properties. And if I go like this, it will bring up the help on blip, which is very sparse. It's a very simple class and so on. And it doesn't have very much going on in it. But it becomes self-documenting when I do this. Well, that's nice. What if I just come along here and I just say balloon equals blip? So let me come here. Let's execute that now. And I'm going to add my 2 extra balloons. I'm going to add my sensors. I'm going to create the array data, and I'm going to compute the angles of arrival. I get the same angles of arrival. I get the same plot we had before. But now my balloon is a 1 by 3 blip array. And I can say, show me balloon of 1. I can say, show me balloon of 3 dot range, and so on. So you'll notice now I'm using regular indexing with the parens as well as the sort of structure indexing with the dots. So the nice thing is my analyzed data, everything else just worked because the notation is the same, even when I changed my balloon to the class blip. Now, what else might I want to do with this class? Well, I might, I have 3 balloons. It might be really a pain to dig through the signal and find out what the actual angle of arrival is there. So what I can do is I can come back to blip now, and I can add some methods. And one of the methods I would like to add is, and you do this in a methods block, I'm going to put the methods and end in first, is you can basically do whatever you want here. I'm going to make a function. You basically program these almost the way you program regular MATLAB code. I'm going to have a function. It's going to take in the object, and that's the only thing it's going to take in. And actually, that's going to need to be an input. The object that we're talking about is going to need to be an input for any method that we create, with one exception. And I'm not going to get to the exception yet, but I want to write the identify code. So let me say my identify code is going to be disp. I'm just going to display, hi, I'm a balloon. Well, let me not do that. I'm friendly and arriving at my angle of arrival, degrees, don't shoot. Okay, so I've got that right now. So now let me save that. And now let me say, let me show you a couple things. Blip, not blip, balloon. When I do balloon dot, if I hit tab, you'll notice not just the properties, but now identify is in there. So I can call identify. Well, for those of you from other languages, you're used to this probably. I can identify, well, I actually have to pick a balloon, not just one. So let me do balloon of one, identify. And then since I'm calling a function, I'll go like that. And it says unrecognized variable. It doesn't know what AOA is. And in fact, if you look here, I'm going to show you the whole thing. I have some messages, warning messages from the code analyzer, and it's saying that the object isn't being used. Should it be a static method? If you don't know what that is, don't worry right now. And I have another message that's saying confusing function call. Did I mean to reference the property AOA of my object? And in fact, I did. I really want the AOA associated with the object that we've got. And to do that, what I do is I say, give me the object's AOA. Once I do that, you see all of my code analyzer messages get better. And now I can come back here and we can identify it, and it's at -10. For those of you who aren't used to OO programming, I can call this like a regular function though. I can say identify balloon of 3, and it just works that way. Okay. Now there's something else interesting. Notice when I had to fill in my parameters for my balloons, I had to create my balloon first, and then I'd had to say its AOA is this and its range, and I had to do all these assignment statements, 9 assignment statements here for 3 balloons. But what if I know the answer right in the beginning and I want to set them up right away? Well, I can do that in Blip. Because one of the things that the class has by default is what's called a default constructor, which is one that you don't need to write. And that's what let me say balloon equals blip. It let me just create one, even though I didn't say anything about it, and it just created an empty one. Well, I'm going to create, whoops, I need this in my methods. I want to put another one in here, and I'm going to say function, and it's going to have an output, obj equals blip, blip. And I'm going to have as possible inputs an angle of arrival, a range, and a signal. Yes, signal. And I'm going to put the end on this function. And then what I'm going to do is, if those come in, I'm going to say obj.aoa equals the AOA, that's the input to my function, obj.range equals range, and obj.signal equals signal. Save. So now I could say balloon, oops, I could say, yeah, balloon of 3 equals blip of 25 and 1 e to the 8. Was that? Yeah. And, whoops, signal. And I get to do that all in one call. Notice I'm trading the 3 calls for 1 call here. Now, if I might want to sometimes have that default constructor, then this won't work all the time. It was only going to work when I have 3 inputs. So I can simply go if nargin is equal to 3, and end that if statement, end it. And then I, Control A, Control I like to make things indented nicely so I can save that. So I've got code now that will create the class, let me put preset values in when I create it, and do the identification. What we did is we defined a class. From the class, we were able to create the balloon object. What I didn't show you, though, is something really cool. I forgot to show you this. Balloon of 1 dot AOA equals 13. It can't. It doesn't recognize it because that's not the way I spelled it, because MATLAB is case sensitive for these sorts of things. So I prevented myself. Remember in the beginning, I changed the num detector. I used num detectors instead. I can't make that mistake anymore. It's going to catch me. And yet I don't have any code there specifically doing the argument checking. It's what I get. That's part of the value of the class. And so, so I created a class with properties and methods. Everything still works so far, but the bad news is, if we take a look in my class, I've still got AOA, range, and signal. And if I think about the sensor, whoops, the sensor here has everything else exposed, the signal and sensor both, but the sensor here, where'd my sensor go? Here, have everything exposed. Now, these might be parameters that a particular manufacturer uses, and they may have several different ones with different sample rates or something like that, or maybe they even let you change the sample rate of your own equipment that you bought from them. But another vendor might make a sensor array that doesn't even have some of the notions of this. Maybe it doesn't worry about spacing or sensitivity. And we've exposed all that information to the users. And so we've maybe exposed more than we want to. One of the things that you'll find if you notice and you use any classes that come from MathWorks toolboxes, we deliberately hide some of that stuff. We don't want to hide anything that will impede your using that particular class or creating objects that are useful. But what we will do is make sure that you have access to everything you need, but we try to hide the rest. So if we change our mind later about something, about how it's implemented behind the scenes, it won't break your code because you can't be depending on something that you can't get access to at that point. And that gives me a segue to what I want to talk about next, which is we have all of this information. We have the number of sensors and the sensor spacing and all those different things and plotting the results. And maybe that's not stuff that, in the middle of all this, I need to synthesize the measurements. I'm going to be computing an FFT. You don't need to, the end user doesn't need to know all of this stuff. They might need to compute AOA. They might not need to know specifically how we do that with the determining peaks. Maybe there's some other method of doing it instead. And so what we'd like to do is basically change the interface to be the smaller number of things that we need. This is just the parameters here, and these are, which is the properties, and these are the methods that we might need for the sensor. And all of the other things that were in there, parameters or methods, are internal to there, and it should simplify the use of the object for you, because this will be the only part that's documented, not all of the other pieces. And so now when I make something like this, it becomes a really nice building block for me. While I'm doing that, I also might want to control, how do I control that? Well, I control it with these attributes that I'm going to use. You can see that I can make the access public or protected. I can make the modifications either dependent on one another, if two things depend on one another, or constant. So there's a bunch of things that I can do. So let me, come over to here. Whoops. My mouse are not getting along now. I'm going to come back to my project here, and I'm going to come to number 3. And actually, I'm going to come to number 4, I think. Number 3? No, I'm going to, whoops. Here's my blip. That's my blip. This is its blip. Yeah, I'm going to come over to part of project number 4 to show you something about encapsulation. So I have my blip. You can see there's a class def. That's the name of the file, has to be the same as the actual class name. And I've got my properties and I've got my methods here. So it's basically what you saw me have before. It's got that if nr n equals 3 constructor. But now I've turned my sensor into a class as well. And what I've done is I've put in some checking because the number of detectors actually needs to be a scalar. So it's going to be a 1 by 1. It's going to be double. So it must be and I want to say it has to be an integer and must be positive, because we don't want our to have -3 detectors. 0 padding must be integer and positive. And you see I can set default values for them here. But now some of the other properties of that sensor, we don't actually need to make public. And so what I'm going to do, and by default, they are public. So what I'm going to do here is I'm going to keep this part private, and I'm going to make a new properties block, properties, and I'm going to go like, whoops, like this. And I'm going to simply copy and paste, and I'm going to make the properties gettable so people can read them, but they won't be able to change them. So I'll put an end on that. And then I'm going to make another properties class, because properties, and we'll do the same thing, but because I want these to be, they don't need to know that underneath we're using some the speed of light, and we don't want them to change it anyhow. And now I'm good. So I've got, you see, I'm controlling things like default values. I am protecting things in this case so that people can read them, but they can't change them. These they can read and change, but they're restricted in certain ways. And then these are things that they can't do anything about. And I can do a similar thing with methods. And I can have, for example, the wavelength and the frequency are dependent on one another. So I could actually come here and I could put in getter methods. And what this allows me to do is say that there's some dependency here. And in order to do that, I actually have to come here And let me come up here and put an end on this, and let me do properties. And where to go? Dependent. What doesn't it like? Right, it doesn't want these values anymore since they're dependent. I take that out. And now I have a blip class that is, if the spacing changes somehow, we can calculate the wavelength and vice versa. They're related here. So we get information. And I have some other methods. I can have the compute AOA method, and I want to make that one public because we're going to need that for the sensor. And I need to create the sensor signal because of creating the synthetic data rather than getting it in the field. And then I could make these other methods protected if I want to. I'm not going to spend the time on that right now. But you'll notice that now I have the speed of light being constant. So let me come back to my analyzed data here now, and let's come and run this. So let's clear everything. Let's do signal. Okay, and now let me come back here, and we have our signal, which is the speed of light. And I can say signal dot speed of light equals 34. Oh, it shouldn't have let me do that. Did I save this? Oh, I have the old blip. No. I did that. I did something silly. Well, here's my best way out of something silly that I've done. Let me come here because I've got it in here. And if I look here at my sensor, now if I use this, I've got my analyze class. Let me clear everything out here so you can see it. I'm going to run here. I've got my signal dot speed of light equals 34. Oh, it's still letting me. I must not have set that properly. Okay. Oh, that's the signal. It's the sensor that I was doing. Sensor dot speed of light equals 34. Oh, it's still letting me do that too. Okay. Oh, because I have the old one. I didn't run the new code. Sorry, I am confusing everything here. Let me come here. Well, let me not worry about that right now. I'll show it to you in a minute because I want to go on to the next topic, which happens to be, well, first of all, let's find out about attributes. I'm going to say property attributes. So what kinds of things can you change here? And you're going to see I'm looking up property attributes in the documentation. Comes up with a nice page here. And you'll see that properties from MATLAB, I can set whether or not to a different value, abstract classes, meta information right here, constant, dependent, and a bunch of information, a bunch of different things, whether or not you want to allow partial matching. So if someone doesn't type the whole thing, they can move ahead. So a bunch of information in the documentation. There are many, many examples in here. You'll see that there's properties, there's class definition, there's programming, and there are plenty of examples when it comes to this. So if you come to the examples here, you might want to look at some of those to help you out too. Okay, so I want to talk about inheritance, and then I'll show you a little bit more about the properties as we go. So suppose I have, right now my blips or my balloons are stationary in the sky, kind of like a weather balloon or something like that. But what if one of them gets the string cut off and it's moving along? It's still a balloon, and I can probably still find the angle of arrival from it, but it's going to be changing over time. So if I have something that's moving, that could still be a blip, but it's just a different blip than the way I've programmed things for. But it has many things in common with everything I've done before here too. And this is where we get into inheritance. Rather than creating a second complete body of code, what I can do is I can say my moving blip is still a blip. So use a lot of the goodness that we've got in our blip class, and then take advantage of that, and then add the differences or the extra things that we need for the fact that it's moving now. So here's an example. If we have our main class, the base class is employees. We all start off with name, address, and department. And we might have two different kinds of employees, a salesperson and an engineer. And there's different information that we track on them. The salesperson might need to have associated with her or him a region and their commission structure, and an engineer would need her products and her team. And there might be another subset under there. Underneath engineer, there might be a specific kind of test engineer that has assigned to him or her the test stage that they're using. And so I don't want to throw out everything. I want to have these also include the name, address, and department that they're in. So the way I do that is I could say I can make a class def engineer that inherits from employees, and a class def test engineer that inherits from engineer. Now, I want to take a little side tour for the moment, because the way MATLAB works and the way classes work are important in terms of understanding when MATLAB makes a copy and when MATLAB uses something, even if it seems like it's a copy. So if I type this, A equals 4, B equals 3, and now I say, no, and B equals 3, let me say B equals A, and now let me say A equals 3. What value is B? Well, if you saw before, the last time I assigned it, it was 4, and yet I just changed A, but it came from A. And so if I look, it actually kept its value 4. So it keeps its value. But what if I do something like this? H dot, let me make a line in a plot. Bring up our plot. Here's our handy plot. I'll put it over here. And I'm going to say, here's a capital H equals our lowercase h. And now I'm going to say capital H dot line width, equals 15. Notice how that changed the property over here. If I say that was capital H, show you there, that was capital H. If I say H dot line width, what do you suppose it is? Is it what it was originally, which was 0.5? No, because it actually is capital H and lowercase h are actually very closely related. They're references for the same thing. It's because our objects, our graphical objects, are part of a handle class in MATLAB. And a handle is a reference to a specific object that exists. Values make separate copies as they go, although we do a lot of things about making sure we don't make copies. Really, we make sure we're very parsimonious about it, but you can think about them each as if I say A equals 3, B equals A equals 4, it's as if we make copies all along. And so a deep copy, whereas the handle just inherits the whole behavior and the whole aspect of whatever was a reference. So you'll find that most objects in MATLAB, most classes, are value ones. Like anything numeric is likely to be that. But most things you write and things that we write that are graphics or file system things, they may well be handle classes. So why use them? Okay, well, I think I showed you that. Let me think about what we want to do here. So remember, I've got my sensors here. Let me see if I've got a plot for that. So in this case, I want to make a new class because I want to make a moving blip from a blip. So you're going to see that I inherit from blip. And the extra property is the amount it moved from in one step, whatever that means. Okay, and my moving blip is going to have some information in it. It allows us to re-envision and re-implement things from the superclass, the class that we're inheriting from, but it uses a lot of the code that's already there, so we don't have to rewrite the code. And really importantly, if we find a bug in that code or a behavior change we want to make, you get it automatically in the subclass. And you can also, as it turns out, inherit from the base classes in MATLAB also. So let me come here and show you this. So I have the class, the moving blip. Now the moving blip, as I said, is inherited from blip. I'm going to clear and close everything right now. It's got one property, or does it? If I make a moving blip, does it have one property? Well, remember, it inherits from blip, and blip had 3 properties. So let's say MB equals moving blip. It has 4 properties. It's got the original ones from the inherited class, and it's got the new one, the delta AOA. And you can see that the way I create a moving blip, I have a constructor here. And my moving blip says, basically, get the object, the information from the extra parameters in case someone passed them in, and put them into our object. But we want to take the last 3 and call our superclass. And this is what I do to call the superclass. I say from my object, my moving blip here, call the superclass blip, and call it just with those final arguments. And if the number of input arguments is greater than or equal to 1, which it hopefully will be, we want to fill in a delta AOA value. And then it's got a method called move. And notice that to move it, what I have to do is I have to somehow say what happens to the object. And I have to say that the object was at AOA, and its new AOA is its old AOA plus the object's delta AOA. And then we just move it and negate it after a while so that it doesn't move as we go, because I'm going to show you how I want to use this. Blip did change. The only change here is we made it a handle class as well, and everything else is the same. Now let me come to analyze this. So we come here. This is the code. Whoops. I'm trying to run something that I was not on the right line. Okay, so clear everything, set up our signal, set up our blip. Now notice here that because a blip is not a moving blip necessarily, it might be, but it might not be. But because these things might be different, I have to put them into some other data type that will let them join together. And so I'm putting the blips, each of my information about the aircraft, into a cell in a cell array here. So I've got 3 blips now. And if we look at balloon, oops, see, it's a 1/3 cell, and we can do balloon, and I can get the contents out of number 2. And it will show me that it is a blip and all the information. And I can get number 3. And what you'll see is that it's a moving blip. Okay. And now I need to create my sensor array information, and I need to create the angle of arrivals. And now what I'm going to do, and the angle of arrivals start off at the original positions, roughly -10, 20, and 25. And I'm going to park this in here for the moment. And I'm going to make this a little bit bigger. What you'll see is now I'm going to move my balloon in a loop here a few times. So let me run this and watch the plot as we go. And you can also watch the output if you want. Well, no, there won't be any output there coming out. But you can see it is keeping the 2 in here in place. And then it hit to near -65, it got too big. And so it went back and then forth again because we were moving it. Remember, I didn't want it to get way far away from the other ones. So we moved it so that you could see that one update as we went. And so I could then call the move function, and that's with a pretty minimal amount of changing to the code that you have. So I want to come back to the slides and just remind us that the subclass substitutes for the superclass. Remember, I was able to use a moving blip for a blip. In this case, I did change everything in this case to a handle because I knew I might want to combine blips with moving blips. And by the way, because this is a moving blip, I can come into my moving blip. I don't need to return the object because it's a handle class. So if I take this out right now and run it again over here, just this section, it works because being a handle class, I don't have to return it as an output. It's changing itself. And you're seeing that happen right there. If it were a value class, you absolutely need the output there, back here, the object equals move of object, because otherwise it doesn't update the object because it needs to be in the output. Okay, so we really changed a very small amount of code to get some extra new functionality to allow these things to be free ranging. And now I'm just going to talk very briefly. I told you about inheritance. There's this notion of events and listeners. So suppose a balloon comes untethered. Should the balloon be responsible for telling everyone, hey, my tether let go? Or should anyone who cares be listening for it? And we think that what should happen is the balloon should just issue basically a message and say, an event and say, hey, I became untethered, and say a name of what it wants people to listen for. And anyone who wants to, any other classes, anyone else can listen for that event. And that way your balloon, your blip, does not need to know about other classes that someone may build in the future that want to take advantage of it. It's just saying, here's events that you can track on me, and then it's up to you, whoever you are, to actually put a listener on and say, did something happen? And then if it did, then you get to do and make some changes based on that. And there are some examples in the documentation for that. So I haven't covered everything, but I just want to go over and over quickly and show you a little bit more. MATLAB has been fully object-oriented for well over 10 years now. Class definitions, methods, and properties, we showed you. Events and listeners, I just talked about. I didn't show you overloaded operators, but if it made sense, we could. Overloading operators and function names. So for example, if I wanted to, I could create a plot method for balloons that would plot them, and I could use the name plot, and it wouldn't interfere with MATLAB's regular plot function because this one would only work on blips. So you can reuse good names if it makes sense. I can change the access of properties and methods. You can have handle classes and not just value classes. There are destructors as well as constructors. So when something gets deleted, what else do you need to do? Well, an example why you might need that is if you've opened a class, a file as part of your class action, your destructor might want to close the file gracefully. I've showed you right now classes defined in single files, and my file was getting a little bit long, but there are ways of taking that and breaking it apart into multiple files if you want. We also have static methods, and I showed you a little bit about property validation. You can use packages to control the namespace, but already, even without that, the classes, by having things protected or protected, you can actually keep the namespace somewhat limited in MATLAB. You just expose what you want. And you can have object arrays. And the nice thing about these are they behave like regular MATLAB arrays. They obey regular MATLAB indexing. And if you don't want them to, you can program that in as well. If you're interested in doing more with this, I already said many of these things. We also allow you to have heterogeneous arrays and mix-ins. And what a heterogeneous array would allow me to do, for example, is to put blip and a blue moving blip into just one kind of class like we have right here, and use regular concatenation rather than having to put them in a cell array. And if I do that, it makes the notation a little bit simpler, but it depends on what you need, whether that makes sense and is really important for you. You can always inquire about information about the class on an object or on a class. And I already mentioned custom indexing. We also have some help for you in terms of testing, doing unit testing on your classes. And if you're interested, we have a MATLAB training course on object-oriented programming that, of course, goes into much more detail than I have just now. It's a 2-day course, and you get to practice a lot of this. And of course, these days, it's also available online. And depending on what university you're at, if you're at a university, you may well have access to MOUTs, which would give you access to an online version of this class. There's also additional resources in the documentation that I urge you to go look at. The documentation is very good and very complete, I think. Doesn't mean it couldn't always use more, but it's been able to answer my questions when I bother to look. And I now want to just finish. I want to thank you very much for joining me today. It's been a pleasure, and I hope you learned a lot about OO. I want to point you to 2 events in the links below on the YouTube page. The first one is the MATLAB Expo 2020 on demand. It's an online site featuring technical talks covering a broad range of topics where MathWorks products play a central role. And if you're interested in more about Simulink, we currently have a Simulink Student Challenge in process, and you could be the winner of $1,000. And please also don't forget to subscribe to the MathWorks channel to get reminders for events like these. Thank you so much.